Hello, good afternoon. April 29th, 2023, Seattle, Washington, about 5 in the evening, Saturday. Here we've been reading the Albert Einstein's Out of My Later Years. And what it includes is a variety of essays, an opening of sorts about his feelings about the affairs of man and his origin, and the middle part, which reflects what is an important thing that is Einstein's final word on Einstein's theory of relativity and our Einstein's theory of relativity, including special relativity and general relativity, and the usual principles that comprise these matters of factual discourse. What describe are the stated axioms and principles of said theory, that what with regards to the constants and the concepts and the context involved should very well reflect what then is an authoritative, and if I read generously enough and thoroughly enough and correctly enough, a fair interpretation of Einstein's opinion So we began reading it, and it started with the definitions of relativity. This is always nice when you want to know something like, I hear relativity is all science. Well, it's half. The other half is called quantum physics, and together they make what's called all kinds of field theories, or a field theory, where the grand unified theory is supposed to be some theory that's physics. That it isn't a fragmented maze of different rooms, each with their own little parlor physics. Instead, it's foundations, results, physics. So, Einstein, of course, is most famous for theories of relativity, special and general relativity, which help to explain things like precession according to gravity of Mercury at the fringe of its orbit, kind of a way, and respects with the things with respect to length contraction and time dilation, or space contraction, as they put them together, about the conservation of energy as a quantity after mass energy equivalence is demonstrated, and that charge it affects the transition and change in energy and reflects potential energy. That is discussed how that's in terms of complementary fundamental quantities, mass and charge, that interchanges energy and balance in terms of energy, a unified charge, though they have their various force carriers, the atom for the kinetic. When you have a fall of gravity, that actually makes it so that there's a theory of gravity with the atom in the middle, and the atom is the real graviton, and atom is his own virtual particle, and And then for the electrons and electron holes, that is charge, and that's the force carrier. Electrons and electron holes are what result the potential of the field. For electromagnetism, where basically that's always an effect of the electric field on the kinetics according to the charge and the rigidity, or the poles of magnets in media of materials. That it was kind of neat to read that and read how free it is from a lot of the clutter of the what you would call continued accommodation of farther and farther afield theories that don't really relate in terms of that. And then there was discussed E equals mc squared, the most famous formula in physics of the 20th century, and a touchstone of scientific education, or in a general education, a usual exposure and familiarity with concepts of science, the practice, and science, the study. And it was discussed its mathematical principles, fundamentals, derivation, and alternative inferences, which fill it out a bigger picture that is as more relevant than a less full picture. And then there's discussed gravity in space and time, and how he carefully delineates what are his principles in his theory about that with respect to otherwise any other models of it, and explains how he embodies in his principles in his theory of physics a model philosopher, a model physicist, and in this manner makes for an abstraction of sorts that Einstein's man, Einstein's always willing to stand in for himself as Einstein's man, and that he doesn't necessarily need to have to philosophize to carry out his purpose, which is this practice of physics, and here establishing the validity and the concepts and what would comprise the falsifiability and lack thereof of Einstein the man's physics, or a model philosophizing physicist's model physicist. So that's kind of what I took away from the notions of gravity, space, and time, that otherwise there's a strong defense of Newton and for finding the empirical force laws that apply, and also a discussion of why, when we think about the geodesy and how it can be that space-time is curved, and why doesn't it restitute, or what bends it back to shape, the absence of objects in the geodesy, or as if after a region of space, this space and time, that when objects leave them, that so do their curvatures. So something must be going on to affect a work in those senses. Here the idea is that it's a fall gravity. After Fadio and Lesage, their theories of the ultramundane corpuscles, they're super classical, and that they represent this instantaneous flux, but do so. That this helps explain how things can be like gravitational waves, and what with regards to those being predicted by these theories like relativity, and also about how they can affect what is non-local transport according to these ultramundane supertachyonic particles. This would exist if such a theory as this kind of supergravity called a fall gravity exists in physics. And that, of course, it has to first not be falsified by all the existing data, everything that's ever validated according to the data and the configuration and energy of experiment, in what it means in the terms as what's so derived would have the physical interpretation, thus an attachment to the models, thus that according to the mathematics that the predicted values exist and are sensible and fungible and tractable to arrive at that all the data still lines up, right? That this notion of the approach to resetting the foundations to accommodate gravity in the theory with relativity and quantum mechanics then has that to explain, and also the quantum physics to explain as a continuum mechanics. So that's pretty grandiose, but luckily Einstein is a real grandiose hedge. And after his tremendous success with relativity theory, then what he really worked on a lot was reconciling that with quantum mechanics and ensuring its priority, and also studying the total field theory. Einstein's greater study for throughout the latter part of his entire career was his total field theory. And so there's not too much that I know that it kind of declares, this is Einstein's total field theory, except so much in these readings out of my later years. This is some of the best encapsulated material I have with respect to Einstein's total field theory. Not that there aren't others, but there is one. It's a total theory. So, and whenever we talk about absolutes or universals or the total, it's quite grandiose. There is some discussion of the Machian and Ernst Mach, and who is described as, with regards to Mach 1, the speed of sound. It was once assumed that anything going faster than 60 miles an hour would explode. There was a model of a time that expressed something in terms of like the vibration that accumulates in the model apparatus, that once it reached 60 miles per hour, it would explode. Then in the speed of sound, it was once assumed, after it was figured out and established that there is a speed of sound, that it was once assumed that anything that goes faster than the speed of sound would explode. Well, and it was once proven that bumblebees can't fly. The latest and greatest in some models of aerodynamic effect, according to Bernoulli, and according to lift, and according to drag, and according to power, and according to work, and according to effects in the gaseous transition phase, according to the flapping of the bumblebee's wings, that it's not, according to theory, a model exists where that they can fly. So here Mach 1 is still tremendously fast speed of 770 miles per hour or so, given that it's also varies according to the humidity in the air, the density in the air, or the height above the earth, where the density of the air diminishes as the height rises above the earth, down to the outer bands of the stratosphere, where basically the gaseous mantle or the air of the earth ends in space and kind of sits underneath what's the ionosphere of all these magnetic currents that surround the earth in a sense. But that anyways, bumblebees can fly. At some point in time, a train or something did go 60 miles an hour and did not explode, although many efforts to arrive at that so failed and blew up. And then there was, at some point in the time Mach 1 was achieved, I forget if it was in the X1 jet. X is the usual designator for experimental aircraft. So the X1 was after that designator became the designation. In the United States, I'm not sure if that was that or not, or the F-104 Starfighter or something like that, achieved Mach 1, and is discovered, and predicted, and whether or not that's so, establishes that the resonances and the interchange in effect makes it so that it builds up such a resonance about it in terms of the speed of the sound and the object through the sound, that it creates this compounding resonance called sonic boom. So when you think of that, and then in terms of that, according to Einstein's theory of relativity as it's most usually interpreted, no object can appreciate to the speed of light, which is a constant, it's fixed, because mass energy equivalence would arrive at that. The energy to so reach that would go to infinity. And the mass would go to infinity, and thus the energy to accelerate it any past that would go to infinity. So it's a boundary. So then the idea of, according to space contraction, something like that to happen would make it similar to a warp wake, or as in the metaphor, and similar to the sonic boom, gravitational waves, as so make for this kinds of things. But that being is just an abstract kind of gedanken, a thought experiment about something like the relativistic nanogyroscope array that all spins up according to Sagnac effect, draws down the speed of space-time locally. You boost it off with a lever, it drops down. All of a sudden, its relativistic mass decreases, but it still has the same energy, and it flies off. Or otherwise, considerations about changes in locale with respect to otherwise dynamics in the relativistic mass energy equivalence. Like, for example, if you had a black hole and were able to put into it a highly contrived bubble on the outside, so that then it would come out, that then when the relativistic dynamics pulled it back out, that it would come out the other side. These are gedanken that are available according to relativistic dynamics. Of course, they represent the utterly contrived in a lot of senses, and the only usual available experimental laboratories for these are this sky survey and the observatory of far away galaxies that, according to the light which was sent here millions and millions of years ago, usually according to their millions and millions of light years distance, that it can be observed in these massive interactions of highly kinetically nonlinear, and as to why this relativistic dynamics result, and these kinds of things are verified according to usually the sky survey or their effects in the geodesy of the apparent. Okay. So with that be kind of being the awe-inspiring side of it, then where we were at with the gedanken was that Einstein's on his train, because he usually introduces the gedanken as being on a train station, because that expressed at the time like the train with the train locomotive and the entire train of cars was the manifest embodiment of these dynamic level of configuration of experiment. It's on straight tracks, it goes very fast, it's basically an unstoppable object, and this kind of thing, vis-a-vis that it comes and goes and stops and starts, and that visually, with regards to light in that sense, and usually is expressed being so indifferent to such small distances that signals effectively can be determined ordering in time at two different locales according to that Einstein usually frames things in terms of the train and the train station, and boarding and deboarding the train, and with regards to the scenery, and usually an observer or two mutual observers. So this gedanken here is the teacup. So in the train there's a car, and it's the commissary car or the diner car, and otherwise a usual sort of day train has passenger seats, if not compartments or something like that. And then in the commissary car there's also tables, and the idea is that the train's motion, once it gets going, keeps things steady inside. When it achieves 60 miles an hour, it does not just blow up because it's shaking much too violently to keep a straight line. And when it gets going, according to this relative motion, that the passenger on the train has the same frame as the rest of the train. He's been accelerated along with it and is carrying along velocity along with it, and so on. And so you can usually have a cup of tea or coffee or in a saucer, a small teacup in a commissary car on the train. So the idea is that the tea comes with a spoon, and some people do or don't variously adjust their tea. I'm not really much knowledgeable about the culture of tea. I enjoy it. I enjoy coffee. I enjoy this, but it's just a hot drink in a cup that has a small handle made for holding with the finger on one side of the cup. So it's a round cup, and on the side is oriented by the fact that a handle exists on it, and is oriented by the fact that it's open above so that you can pour liquid in it. The liquid maintains its gravitational field, its usual orientation within the cup, that you can pick up the cup and orient it to your face while pouring it into your face and drinking from the cup. And then the other notion is that you can stir the contents of the cup with this spoon, usually because it's much too hot to stir with your finger. And that trying to swirl it around doesn't affect anything that really can get the contents of the cup swirling around without splashing. Because as it swirls around, it will naturally form a disc or meniscus within it that falls into the cup, and that according to the centripetal or centrifugal force, if there's the centripetal in one model or the true centrifugal in another model, establishing a rotation without an instrument inside to stir it would throw it out. So then the idea is that Einstein's general relativity basically is an effect for this linear part, and then for the rotational part, that it's affected by frames that accompany each of these linear frames, because everything's in a linear frame that is this rotational frame. And so that every frame, for general relativity, everything lives in a frame, it's a kinetic frame. There's this. And so this makes for that. Otherwise, what would be the world of singularities instead have an attachment to the theory as just the fact that it's still going to follow from the combination of linear events as a round somehow. So for that, the being the kind of thought experiment, and why not to frame it in terms of like the spinning wheels of the train? The train moves on its tracks courtesy the almost lack of friction by rolling the wheels of the train over the tracks. Is because in that sense they're going in the same direction as the train, whereas stirring the cup is as to either orientation, given that you're always usually facing to the front of the train or the rear of the train. You never find in a commissary car facing to the middle, although sometimes there's a bar and it's usually facing to the side to make way for passageway past it. So this establishes that the coffee cup is the notion of anything that's rotating in the frames, and while being contained in the same frame. So that's all there is to it. It's a thought experiment. And then as relativistic is that with an infinitely deep cup and an infinitely long spoon and an infinitely high speed, that the teacup would bring the train to a halt. Because it would be infinitely massive. So, let's see here. Now, there's quite long, after time, space, and gravitation, which we kind of got into, and then I suppose there was the field concept. And so if we're going to be reading about field, it looks like this is going to have to spread out a little bit more than just this reading. And it certainly deserves it, because what I should hope to do is to actually read through these things. And so we definitely got it up and out of chapter 12 and into chapter 13. It has often been said, and certainly not without justification, that the man of science is a poor philosopher. So here's where this is Einstein, the man, the model of science, the very state of the totality of our sense experience, the aim of science, as complete as possible, an important property of our sense experiences. This is about what we got to, about above the multitude of layers discussed when we're talking about energy and mass and charges. Well, the fundamental layers are kind of underneath that again. The mass and charge become as of an interchange of energy again, why energy is kind of a layer twice for value in its quantity and for interchange and its differences. So, intermediary layers are only of temporary nature. They must eventually disappear as irrelevant. We have to deal, however, with the science of today, in which these strata represent problematic partial successes, which support one another, but which also threaten one another, because today's systems of concepts contain deep-seated incongruities, which we shall meet later on. I read him in that tone as that's not anything less than sincere. Mechanics and the attempts to base all physics upon it. Section 2. An important property of our sense experiences, and more generally of all experiences, is time-like order. Here earlier in the book, Einstein has several times referred to the time. So in that sense, he's establishing a certain affinity towards a notion of a universal time. Is its time-like order. In terms of all the, how you would say, invariances in theory, according to physics, about the only symmetry that's never been violated in physics is time symmetry. This kind of order leads to the mental conception of a subjective time, an ordinating scheme for our experience. The subjective time leads then through the concept of the bodily object into space to the concept of objective time, as we shall see later on. In many theories of physics, time is let out to reflect any other differences. So that when we talk about time and negative time, especially, negative time is just a placeholder for some otherwise anti-commutative or what would become a measurable or a contribution of having analytical character. That negative time in almost all models of physics has no physical interpretation as negative time. Is just a mathematical interpretation to a part of a physical model that, according to then what ends up being attached to the real physical model, So models it as negative time only insofar as that it represents that when it's all added up, those pieces they're missing that adds up to 0. Because all those are to reflect differences either way, that they assume some kind of boundary that they share. So that's just to say that if you've ever heard of negative time in any physical theories, it does not mean backwards in time. It only is a mathematical model. This confuses, enrages, irritates, or deceives some people because they implicitly attach the mathematical model to this physical interpretation, and when anything in the mathematical model also has a physical interpretation that is not underdefined, like time in these theories are, is just a parameter of t, that becomes grounds for ambiguity. So anyways, here it's not. There is a notion of time slowing, and actually not just clock's measurements slowing, but the time slowing, but then that it rejoins, but that's mostly for highly contrived relativistic dynamics, and that they still only go forward together. They forward in time. The subjective time leads then through the concept of the bodily object in a space to the concept of objective time, as we shall see later on. So he's talking about a concept of objective time. Ahead of the notion of objective time, there is, however, the concept of space, and ahead of the latter, we find the concept of the bodily object. The latter is directly connected with the complexities of sense experiences. It has been pointed out that one property which is characteristic of the notion bodily object is its property which provides a coordinate to it in existence independent of subjective time and independent of the fact that it is perceived by our senses. We do this in spite of the fact that we perceive temporal alterations in it. Poincaré has justly emphasized the fact that we distinguish two kinds of alterations of the bodily object, changes of state and changes of position. The latter, he remarked, are alterations which we can reverse by arbitrary motions of the bodies, or their starting and stopping their motions. Most interactions are reversible. Some are irreversible, and this usually reflects a regime as of the composable and decomposable, why entropy for the second thermodynamics law is irreversible in a sense, but in these other ones it's reversible. And then there's the adiabatic and non-adiabatic. That's the usual framework of these things: reversible and irreversible. The latter, he remarked, are alterations. That's not to be confused, though, with that time symmetry has never been falsified. The latter, he remarked, are alterations which we can reverse by arbitrary motions of our bodies. That there are bodily objects to which we have to ascribe within a certain sphere of perception, no alteration of state, but only alterations of position, is a fact of fundamental importance for the formation of the concept of a space, in a certain degree even for the justification of the notion of the bodily object itself. This is called such an object practically rigid. And so with regards to that, usually you see this in regards to the rigid telephone pole and when it goes to light speed and enters the barn, or these kinds of things that go with the deformations and the relativistic with the notions of the length contraction and time dilation and with regards to velocity and And it's having that, on the one hand, that's because, well, we got to preserve the geodesy of this curving space-time as flat to still handle that when we curve it, it adds up for gravity. Space-time is flat. Compared to in a space contraction, that an object moving through it actually kind of brings a little bit of space, only its immediate surrounds all the way through it, that is its immediate surrounds in its frame. But actually the passage and the transit have to reflect the same thing as space. An object is in space. Space is an object, and an object is in space. So these are the kinds of things that when we get to thinking about relativity and motion and the distinctness of bodies, then that's something. And as to why the object is practically rigid reflects that, and also its local space-time. That's not extra. Its local space-time is also practically rigid, but not necessarily that its local space-time and its non-local space-time doesn't emit any differences in the warp and that between that and the space-time of the geodesy, which curves but also flattens back out again and is flat, where, for example, we have a model of gravity is that space contraction is now how the principle of relativity gets absorbed. And from the theory and for all the effects, that it still exists, this stuff, while at the same time gravity is let out with its own explanation that adds up these same things anyways. That also, yes, the space-time is curved from this side, and space-time is rigid and flat from the inside. Well, still it's so that when you have something like a linear accelerator and the particles are accelerated at incredible energies to incredible velocities, it makes gravitational waves right on it and across it and shrinks the space and brings back in there. There's stress fractures in the shell of the thing, the linear accelerator, and it can be partially explained by why this is so. If, as the object of our perception, we consider simultaneously, i.e. as a single unit, two practically rigid bodies, then there exists for this ensemble, a team, a togetherness, an ensemble, such alterations as cannot possibly be considered as changes of position of the whole, notwithstanding that this is the case for each one of the two constituents. This leads to the notion of change of relative position of the two objects, and in this way also to the notion of relative position of the two objects. Change of relative position and relative position. So yeah, this affects it. They still have their motions and their energy with respect to all the rest of the frames. It is found, moreover, that among the relative positions there is one of a specific kind which we designate as contact. So contact is the result of a degenerate orbit resulting in a collision, and we have a theory for kinematics of elastic and inelastic conditions. Permanent contact of two bodies in three or more points means that they are united as a quasi-rigid compound body. This is usually that the rigid is non-deformable and the quasi-rigid is deformable and non-deformable. Here is about forming a space by its motions through the space, and that the very fact that it has relativistic mass at all warps the space as you go through it, and everything kind of is constantly still curving its space, and that it uncurves behind it. That this action of these changes is the course of passage, compared to that the geodesy is state. It is found, moreover, that among contact. Permanent contact, establishes kinematics. So kinetics is a ball, and it moves in a line, and it's got a velocity. And kinematics is a spinning ball, anything to do with, for example, a handle on a hammer or something that's thrown, or some such similar apparatus. Kinetics is modeled mostly as a non-rotating frame, whereas kinematics basically automatically implies a rotating frame. The dynamics or kinematics. As of the jointed and connected, and otherwise like the hinges and skeletal and this kind of stuff. It is permissible to say that the second body forms then a quasi-rigid continuation on the first body and may in its turn be continued quasi-rigidly. Possibility of that quasi-rigid continuation of a body is unlimited. The real essence of the conceivable quasi-rigid continuation of a body B sub naught is the infinite space determined by it. Well, that's strong. Now, the real essence of the conceivable quasi-rigid continuation of a body B naught is the infinite space determined by it. Now, there's a lot of reading into the word infinite here, and it's also it's locality, and also for that means, well, the global is infinite effectively for that, or variously. That the real essence of this is its context. That's the real essence of something, is its context, but I'm not quite so sure how to read that. but he says, and then space is in quotes, is the infinite space determined by it. And so this just kind of reflects back on my comment a bit earlier. It's like the object is its own space. It is its own space. And it travels through space greater, and together that's still one space, but there's just a constant passage in space, modeling coming and going, just as well as being and pointing, as it were, that the geodesy does of general relativity. So the idea is then to solve for these Lorentz transforms with suitably sufficient but simple as possible, no, simpler, way to establish these, that would also add up for the gravitational field equations, that then the cosmological constant of sorts about the curvature could help illustrate in detail then how in the Galilean that what happens when things accelerate hard by light speed, that this is how they behave. Now there's a footnote above with regards to contact, the notion of collision or contact, or here that there's contact as of two objects that were not connected in their contact, and there's two objects that as are connected into one object, that were their contact broken, they would be two objects that are considered one object. Insofar as whatever is rigid transfers all strains and stresses applied to any point on the shared overall object to every other point, according to the utter rigidity and inelasticity of these things and non-deformability. So as footnote says, it is in the nature of things that we are able to talk about these objects only by means of concepts of our own creation, concepts which themselves are not subject to definition. It is essential, however, that we make use only of such concepts concerning whose coordination to our experience we feel no doubt. So this seems to be part of our grandiose hedge, and he's saying that he'd rather fill in more detail with regards to this kind of thing, and that he basically would have to further define these objects wherever they're underdefined, that basically the domain defines these according to whatever extensions the domain exist. And he's saying that by no means is this to be interpreted as fully defined or complete, because he's kind of spooked out by it, because doubt spooks him out. The very name geometry indicates that the concept of space is psychologically connected with the Earth as an assigned body. So wait, now I skipped some here. In my opinion, Einstein's opinion, the fact that every bodily object situated in any arbitrary manner can be put into contact with the quasi-rigid continuation of a predetermined and chosen body be-not body relation, this fact is the empirical basis of our conception of space. In pre-scientific thinking, the solid Earth's crust plays a role of be-not and its continuation. The very name geometry, the world measure, geometry, indicates that the concept of space is psychologically connected with the Earth as an assigned body. This is often called the terrestrial frame. The fact that all our we never got on and off this train. Every human being on Earth that is from Earth and was born on Earth and spent their entire lives already in the terrestrial frame. So it's quite different than thinking that there could be a particular contrivance that enables someone to jump all the way to outer space because there was another mirror planet just for a while put up above it, that because of the balance of the gravity we could leap back and forth between them. Such things are not part of our scientific dogma at all, because it would be utterly contrived to imagine such a situation and unavailable to resources. Now, as a comment earlier that was made about materials, is that according to material science, according to the strength of materials and their physical properties and their properties of all sorts of things having to do with pretty much anything, it's been quite some time since, according to like how many gigapascals does a thread have to be that it can handle with regards to tension and this kind of stuff, there was said that given enough money input, any material can be made. Any material can be contrived. Here, though, that is not really relevant at all, because anything that's relevant involves a simple terrestrial experiment, like the behavior of pendulums during an eclipse, or a simple sky survey experiment, like the observation of the dual neutron stars according to relativistic dynamics, and as well of course, the solar observatory of the planets, that so indicated by the well understood masses of these planets and their orbits that are soon to not be dynamic, but in fact it's a matter of the relative equilibrium, that these are the things that are to add up for our astronomical calendars and such. And also for anything else, really, because when it gets down to it, that there's notions of momentum and all this stuff that comes up out of relativity that really makes for solutions that affect things even in the small. When something hits 60 miles per hour, maybe it really would blow up, or there's relativist effects, if not significant, become observable even in such notions of space-time as the terrestrial. The bold notion of space, which preceded all scientific geometry, transformed our mental concept of the relations of positions of bodily objects into the notion of the position of these bodily objects in space. So space here, and he's put it in quotes each of these times, means this space of relativity theory that is the backdrop of our geodesy, and it's just in effect whatever goes linearly. And the way it's curved affects how things take any course that's otherwise linear. And the highly nonlinear is the dynamic, and anything that's actually rotating is essentially treated as just a linear body with respect to any contacts that occur, because relativity is, in the sense, having that the highly nonlinear is the singularities, and then the idea of this gedanken and attaching the white holes everywhere and in our Dirac positronic sea for relativity's sake in the space is still for the same space for Einstein's total field theory, filling it out. This, of course, represents a great formal simplification. Well, sure it does. It's a wonderful, grandiose hedge. Through this concept of space, one reaches, moreover, no longer in quotes, an attitude in which any description of position is admittedly a description of contact. So this is local, because when two objects that are actually touching are they at least share that part of their space. Two objects that are not at all touching have at least some difference in their space, is what he's saying. Through this concept is admittedly a description of contact. The statement that a point of a bodily object is located at a point P of space means that the object touches the point P of the standard body of reference P naught. Supposed appropriately continued at the point considered. In the geometry of the Greeks, space plays only a qualitative role, since the position of bodies in relation to space is considered as given. It is true, but it is not described by means of numbers. Descartes was the first to introduce this method. In his language, the whole content of Euclidean geometry can axiomatically be founded upon the following statements. 1. Two specified points of a rigid body determine a distance in their local space. 2. We may coordinate triplets of the numbers x1, x2, x3 to points of space in such a manner that for every distance p naught minus p naught naught, or p prime minus p prime prime under consideration, the coordinates of those whose endpoints are x1 prime, x2 prime, x3 prime, x1 double prime, x2 double prime, x3 double prime. The expression s squared equals x1 double prime minus x1 prime squared plus x2 double prime minus x2 prime squared plus x3 double prime minus x3 prime squared is independent of the position of the body and of the positions of any and all other bodies. So this is a representative of the quadrature, it's a representative of the Laplace's equation, it's a representative of about the acceleration, and for Newton's first and second laws and third law, and that I kind of would rather rewrite Newton's third law in terms of Newton's two zeroth laws. About that, the higher order acceleration has been discussed here, and some of the talks about the path integral and these kinds of things is kind of the entire flip side of coming to a stop from getting to a start. that the reaching acceleration to a velocity and then decreasing it back has that this formation of what results in the Laplacian for this distance formula for the metric, for the norm, for the distance function, that of course is central and ubiquitous and correct in all our physics, has that I'm really kind of looking at the Laplacian for a very strong complementary dual as what provides that instead of the output being the Laplacian, which is how about the sum of the partials in their square, is a directional vector that is sort of like, well, why don't you take the gradient of the higher order terms when they come together neat? And that indicates that something falling above at a given velocity probably came down the maximum track. This is what I'd be looking to in terms of that this sort of relation is what sort of results derivations that is usually buried many years deep in all the derivations of what's called relativity and many other aspects of mechanics, including the classical mechanics. That is to be retroclassical, and is this potential theory and sum of potentials, and that if harmonic theory is harmonic functions are defined by the Laplacian equals 0. This is a super theory of harmonic theory, that potential theory is not only a harmonic theory or the theory of harmonic functions. There is one. It's great and it's ongoing, but there are others. A complementary dual. The positive number s means the length of the stretch, or the distance between the 2 points p prime and p double prime of space, which are coincident with the points p prime and p double prime of the stretch. The formulation is chosen intentionally in such a way that it expresses clearly not only the logical and axiomatic, but also the empirical content of Euclidean geometry. It preserves distances under transformations. The purely logical axiomatic representation of Euclidean geometry has, it is true, the advantage of greater simplicity and clarity. And so I would say that Euclidean geometry could have, that this is affecting for continuous bodies, the usual continuous transformations without deformation or torsion or ... And then about the rotational that establishes a body, and that these bodies are not rigidly connected. That's fine. But that they are then, in terms of their being in a frame, that still they travel through space together, contracting as they come and contracting as they and relaxing as they go, and that's how it goes. Euclidean ... It pays for this, however, by renouncing representation of the connection between the notional construction and the sense experience, upon which connection alone, the significance of geometry for physics rests. The connection between the notional construction and the sense experience, the fatal error that the necessity of thinking preceding all experience was at the basis of Euclidean geometry and the concept of space belonging to it. This fatal error arose from the fact that the empirical basis on which the axiomatic construction of Euclidean geometry rests had fallen into oblivion. I'm not so sure quite what to make of this about the geometry of the Greeks, the Euclidean, about it's that Descartes' method of the entire content of the Euclidean is built upon this axiom that the Laplacians are the only means to the Laplacian always exists and is well defined in this and that. So yeah, I'll definitely be looking at Laplacian and trying to figure out how that theory of potentials is modeled. It's attained to, and it's a limit of some theories of harmonic and hyperharmonic functions. But really, it's just whatever adds up, everything that provides that it also results the classical part in the middle, but that it is of the potentials, not extra local, the non-local. That the theory of sigma potentials is necessarily uniform in the total. It pays for this. The fatal error that the necessity of thinking preceding all experience was at the basis of Euclidean geometry and the concept of space belonging to it. This fatal error arose from the fact that the empirical basis on which the axiomatic construction of Euclidean geometry rests had fallen into oblivion. Insofar as one can speak of the existence of rigid bodies in nature, Euclidean geometry is a physical science, the usefulness of which must be shown by application to sense experiences. It's the law. It relates to the totality of laws which must hold for the relative positions of rigid bodies independently of time. As one may see, the physical notion of space, also as originally used in physics, is tied to the existence of rigid bodies. I'm not so sure about that, because when you think about Achilles and the tortoise running on the track, they're either on a straight track or a circular track. So I wouldn't necessarily put it that, and so they're distinct bodies and they're non-deformable and they represent a classical motion. They're rigid and they move linearly, but in terms of their course, that they either go around a track or not. And so I'm otherwise agreeable with that when you're talking about the linear components of things, that it's so that they act irregardless of their rotational contents. But it is so that the rotational results are contrived in terms of kinematics. What a contact is not necessarily and usually isn't a linear and absent any nonlinear components. That it could be highly nonlinear with respect to the something that deflects so much because of like a rubber ball, which is deformable, and given whatever way it's spinning, so deforms, yet reaches a point of contact, which is rigid, which is compressed all of its energy into the form, which will deflect it. That makes for any matters that's not geometric ricochet or whatever, but instead the racquetball metaphor example, just as surely to make so that the ball has spin, and that according to any contact it has, that is not absent the classical mechanics so much of these rigid bodies, but in terms of then the space that it's attached to, also it's attached through that. And to keep them both connected is, again, just making for this special relativity is local, and then there's local, and then the space is local, and then in terms of what it comes and goes through, and whatever it affects in terms of its passage to the space warp, it's local to that effect. Local. And so then otherwise for the rotational, then when that basically says, well, it basically inside the space of this rotational, it's reduced that size inside, but it still looks the same from outside, and it still is the same from inside. But it's reduced that space and increases density, and that's how it's working. It's also the same. But here Einstein is expressing that this is a great consternation, because otherwise we need to have what rules add up and out for these rotational and things, bigger contrivances. And bending the rules of physics, bending the rules of geometry, instead of putting a little rule everywhere. Or carrying our rules along with us. Insofar as one can speak of the existence of rigid bodies in nature, Euclidean geometry is a physical science, the usefulness of which must be shown by application of sense experiment. says it relates to the totality of laws which must hold for the relative positions of rigid bodies independently of time. As one may see, the physical notion of space, also as originally used in physics, is tied to the existence of rigid bodies. From the physicist's point of view, now remember this can be Einstein's model physicist, who he can ascribe ignorance. And in fact, sometimes he would be, whether he does or not, is the physicist's point of view and the subjective and the objective here. All right, that subjective and objective are usually enough relative, and not to use that in jest or without specification, reserve. From the physicist's point of view, ditto for point of view, the central importance of Euclidean geometry rests in the fact that its laws are independent of the specific nature of the bodies whose relative positions it discusses. Its formal simplicity is characterized by the properties of homogeneity and isotropy and the existence of similar entities. So here this is basically that any rotating body makes a white hole anywhere, and it makes for the decrease in space terms, decreasing its density, increasing its mass, but yet so keeping the same outside space, that instead of everything falling in never comes out, that everything that goes in comes out. And it's about orbits. Everything is in orbits in the geodesy. It's relativistic, according to Einstein. That seems a nice complementary definition for a complementary dual in kinetic singularities, the kinematic singularity. From the physicist's point of view, the concept of space is, it is true, useful, but not indispensable for geometry proper. What? I.e. for the formulation of rules about the relative positions of rigid bodies. In opposition to this, the concept of objective time, without which the formulation of the fundamentals of classical mechanics is impossible, is linked with the concept of the spatial continuum. Spatial. The introduction of objective time involves two statements which are independent of each other. 1. The introduction of the objective local time by connecting the temporal sequence of experiences with the indications of a clock, i.e. of a closed system with periodical occurrence. 2. The introduction of the notion of objective time for the happenings in the whole space, by which notion alone the idea of local time is enlarged to the idea of time in physics. Local, whole, local or global, right? By which notion alone, the global time, the idea of local time, is enlarged to the idea of time in physics. So here again, without being too overly generalist to the notion, it does seem that Einstein is saying, I have a clock hypothesis, and where anything has to do with time of the clock is local. Now, you might know me because I said there's no spooky action in distance, and here I'm putting all the spooky action in the local, about time. And so, I mean, that is not to be, that's not meant to be satirical, it's not parodical, it's not meant to be unfair or ingenuous, this reading of what I think Einstein might have said, but what it means is what it said. Note concerning 1, the introduction of the objective local time. Each is objective from its objective. He puts both relative terms objective to each other because they're two observers, at least. Note concerning 1, as I see it, it does not mean a petitio principii. If one puts the concept of periodical occurrence ahead of the concept of time, while one is concerned with the clarification of the origin and of the empirical content of the concept of time. Such a conception corresponds exactly to the precedence of the concept of rigid or quasi-rigid body in the interpretation of the concept of space. So here, yeah, what he's saying is that the usual notion is like, well, time never changes. It's only the clocks change. So when we talk about time dilation, we were counting on our clocks. It's like Einstein saying, well, no, you're counting according to your conception, just as you have the same conception of space, which you've attached by these rigid or quasi-rigid connections. And as was discussed earlier in this talk, that this connection of that it's whether it's the clock or the time is what's measurable. All we can measure is the clock, and so that's all that matters, and that is the time is in one sense. And Einstein saying, hey, that could just be periodic oscillations, and when the time really slows because the space really has this change in its extent with regards to that there's no privileged motion in this rotational setting, particularly, and as for how any pendulum clock works and any spring clock works and any atomic clock works, after any crystal clock works, vis-a-vis the measurement of time, and for Hefele and Keating, what it means, the whether and which way around the Earth they went, and then for Pound-Rebka and this, special things, and for the usual notion of Pike's Peak or what, the time dilation that is framed in two different things here by Einstein, and he reflects for his total field theory that it's not the usual one, if I can give that a generous reading. Such a conception corresponds exactly to the precedence of the concept of the rigid or quasi-rigid body in the interpretation of the concept of space. Further discussion on 2. This is his global time. His clock hypothesis, there is a universal time. Drives the geodesy. Stuff coming in and out of space, so it still has to observe it. The illusion, further discussion of 2, the illusion which prevailed prior to the enunciation of the theory of relativity, that from the point of view of experience, the meaning of simultaneity in relation to happenings distant in space, and consequently that the meaning of time in physics is a priori clear. This illusion had its origin in the fact that in our everyday experience we can neglect the time of propagation of light. We are accustomed on this account to fail to differentiate between simultaneous seen and simultaneously happening, and as a result the difference between time and local time fades away. Now, I even kind of have to leapfrog Einstein here a little bit on this one, because I got general relativity first and special relativity, and so I still got this constant speed of light, and it's finite, but I wouldn't want to reflect a neglect on that, just as the classical had reflected a neglect on that light speed was not finite, that things occurred according to it instantaneously, which was discovered at least several thousand years ago, that light speed is not infinite. Whereas, so that doesn't mean that objects in the space, I guess is what I'm saying, according to this general relativity in the linear, are so bound by it that they're still Galilean. So this is kind of a retro Galilean approach, that after Fitzgerald's kind of approach to the Lorentz things that make for space contraction equals length contraction plus time dilation, that time dilation in the linear kind of goes right out, where it kind of comes in the rotational, for example, the singularity of the black hole, and where it's usually kind of discussed about how things stop and this and that. That's where the kind of the big fork in the road is for what I'm trying to have, is that this is still Einstein's course. Either way of these courses are a road to reality to Einstein's way. That it's along these lines of how his expressions here make for it, like so. That's all I wanted to really put forward about this notion of the that is difference was about the special theory and about the L principle, that light speed is finite as constant. I'm not rejecting that. I'm just rejecting the some of the concepts to do with mass energy equivalence of that, because of the Galilean. We are accustomed on this account to fail to differentiate between simultaneously seen and simultaneously happening, and as a result, the difference between time and local time fades away. The lack of definiteness, which from the point of view of empirical importance adheres to the notion of time in classical mechanics, was veiled by the axiomatic representation of space and time as things given independently of our senses. Such a use of notions independent of the empirical basis to which they owe their existence does not necessarily damage science. So here he's really strong in saying, hey, I have a model philosopher and a model scientist, but he is not allowed to rely on anything but his senses. And so the idea that otherwise the axioms come up about like space is infinite and it's linear and it's Euclidean and it has a metric everywhere, it's always flat, compared to, time is a constant, it's constant uniform motion, it's infinitely divisible, and it's uniform and it's straight. That any differences here with regards to the philosophy and the sensory experience says my sensory experience is basically about what it makes for someone applying his participation in the events. So, I mean, here it's almost that he wants to make sure that, yes, I believe in a deterministic world, I'm a scientist, but my free will is not gone away. And I'll close my eyes if I don't think so. Right? And that it's a conscious matter of sense. That's how I'd like to read this, to explain his philosophizing around it, because he's not just philosophizing for himself, he's philosophizing for a model physicist. And so he's saying that that's his desiderata for the modernist theory, the lack of definiteness, ... One may, however, easily be led into the error believing that these notions, whose origin is forgotten, are necessary and unalterable accompaniments to our thinking, and this error may constitute a serious danger to the progress of science. And so he's saying that those are deconstructible, and it's all right. It was fortunate for the development of mechanics, and hence also for the development of physics in general, that the lack of definiteness in the concept of objective time remained obscured from the earlier philosophers as regards this empirical interpretation. I think he's indicating that there's various experimental results that still boggle, and that they would need something more, like this teacup setup, to get squared. Full of confidence in the real meaning of space-time construction, they developed the foundations of mechanics, which we shall characterize schematically as follows. A. Concept of a material point, a bodily object which, as regards its position and motion, can be described with sufficient exactness at a point with coordinates x1, x2, x3, description of its motion in relation to the space B naught by a given x1, x2, x3 as functions of the time. B. Law of inertia, the disappearance of the components of acceleration from a material point which is sufficiently far away from all other points. So he's saying that there's sufficient, that according to some, it's sufficiently far away is rather abstractly let out. But it is nice to see somebody, attacking Newton's first, second, third laws of classical motion, about this some zeroth laws of Newton's laws that end up explaining that then one of them is to see law number 1 and follow, but the other one is that see law number 4 and come back. Law of inertia, the disappearance of the components of acceleration from the material point which is sufficiently far away from all other points. C. Law of motion, for the material point, force equals mass times acceleration. This is the usual definition of force. It's the usual definition of the quantity of electromotive force or voltage. It's the notion of force, what results that any mass that accelerates by any amount in a given period of time must have had such force applied to it. It's the same thing as results that gravity's potential makes for it so that it's always like so. D. Laws of force, actions and reactions between material points, collisions, and this, B, is nothing more than an important special case of C. So he's saying that B, the law of inertia, is really defined by C, the definition of force, which is really just ratio that falls back from quantities under acceleration that can be so input back into other formulas which determine what work is required by such power to be applied to make such force given times that result the wheels go round and round. The wheels on the bus go round and round. And it starts and stops. And this B is nothing more than an important special case of C. And so then it also helps explain why like momentum isn't conserved. It's like, well, momentum is conserved. It's like, how about the angular? It's like, don't talk to me. And so these are the kinds of things that, and excuse me, that was meant to be, that's somewhat jocular. At this point, after talking about the earlier concepts of, Einstein setting up how to be retroclassical again, while also helping set up what's superclassical in this attack on Newton, which is great. That's something that I'd really like to get figured out a little bit more. A real theory exists only when the laws of force are given. Forces must, in the first place, only obey the law of equality of action and reaction, or the system of points permanently connected to each other may behave like one material point. I'm going to stop here, but he does get in next about the Pale experiment, or what's called why there is real centrifugal force. And so that's the reading for today. It's kind of fun, huh? Because when we talk about Newton and Einstein and classical mechanics and relativity and the theory of relativity and about how to extend what still works up these things and how to figure out how it could be that two or three left turns still make a right turn in some of these cases, and that it's still left up as like Einstein's like, this is what I'm keeping, and it's gold. And all this other stuff is kind of like after three left turns, that's what you're left up with, because empirically that's also correct. I mean, empirically, this is what matches the data. I need you to decompose this theory and get it back to what goes into it to make it so that it's a straight left turn. It's kind of what he seems to be describing, in terms of that otherwise he defends very carefully particular points. He gives an abstract observer a particular starting point, and then as well that he gets into like, also here's fundamentally a deconstruction of the laws of motion with regards to that here is fundamentally about the Descartes, Euclidean, the Laplacian, that can be deconstructed. All right, well that seems kind of interesting. And so I suppose there's more to be reading about Albert Einstein, and from Albert Einstein, I enjoy the guy. Hey, have a great day. Bye.